Director in the Powertrain Engineering Division at Southwest. Today, his talk is going to be about achieving high efficiency in heavy-duty diesel engines. Thank you, Jason.
Thanks very much for the introduction. I'd like to at least acknowledge my cohorts back at Southwest Research who helped contribute to this research. I actually didn't do much of the engine testing on this particular program, but they elected to let me present on it anyway. So I'd like to at least acknowledge Radu Floria, Andrew Morris, Zainal Abedin, James Sedanik, and Michael Collins, who were really the strong contributors to this work. So I wanted to begin the discussion with just a quick introduction of Southwest Research Institute. I'm not sure how many of you are familiar with Southwest Research Institute. We are located in South Texas. A few key facts about Southwest Research is we are a non-for-profit organization. My CEO likes to remind me that we're also not for loss. So we still need research dollars and we need to manage our programs well, but the designation is mostly just for tax purposes and to let you guys know we don't actually have any stakeholders. So we're really driven by our statement there. We're here to benefit government, industry, and the public through innovative science and technology. We mostly focus on the technology and we focus a little bit less on making a dollar for the shareholders. I also wanted to mention we have a large facility down in Texas. We also do have a small office here in Ann Arbor to help support local activities. So although most of our labs are down in Texas, we do have some engine test cells up in Ann Arbor as well. So being that we're a non-for-profit and we don't have shareholders, it kind of puts Southwest Research at a little bit of a unique position. We are not a higher education university or anything like that. We're not an engine manufacturer, but we really work with government and industry. One prime example of this is the low NOx program that we're currently conducting for California Air Resources Board. So California wanted to work with somebody that was independent, and they contacted Southwest Research and asked us to look at some of the early demonstrations of that 0.02 gram per horsepower hour tailpipe NOx standard. So that work is being conducted down at Southwest Research Institute. Of course, we work with the industry. A lot of the OEMs, tier 1 suppliers, are very interested in this type of work because it has a lot to do with what their business models are around. But because it's being conducted at Southwest, we are able to work not only with the government side of it, but also the industry side as well. So that's just a prime example of how we partner with both government and industry to try and advance technology. Another way that we work together with the industry is through our research consortium. These are programs that are collective. We have membership and all of the members come together. They pool their resources to try and look at future competitive technologies. These are technologies that are intended to be 5, 10, 15 years into the future. I have the privilege of actually managing one of those consortiums, the Clean High Efficiency Diesel Engine Consortium. And you can see we're very creative. Every 4 years we start a new program and we have to come up with a new logo. So I've got the long history down there at the bottom. But you can see that this particular program has been going on for quite a long time, back into the 1990s. And we've been addressing a lot of the different challenges that come to the diesel industry. Our current program is focused on achieving very high brake thermal efficiency. Our target is 55% system efficiency, which would include some waste heat recovery, and also trying to achieve near zero tailpipe emissions, keeping that potential new NOx standard from California in mind as we move forward with our research. But you can see there's our current consortium membership. I don't know if anybody else has managed a consortium, but it's kind of an interesting job. I have 26 individual companies, which is almost like having 26 individual bosses. Most of the time, they generally agree on some of the different technical directions, but it is a bit of a challenge trying to get the input from all the different members. So this particular program, of course, the drive for engine efficiency, I think this has been well covered by some of my colleagues that have already presented. I'll just very briefly talk about the regulatory standpoint. Of course, the US EPA is regulating greenhouse gas for on-road trucks, and so we've had new phase 2 things that regulations that came out requiring about 6% reduction in greenhouse gas, while simultaneously looking at the new regulation from California. So when you start to consider both a greenhouse gas regulation where you're demanding more fuel economy, and at the same time looking at future NOx regulations, those two combined together make a pretty compelling argument for needing further engine improvements. There are several other programs, such as the co-optimal program that was mentioned earlier, and the Department of Energy. I won't go into any of those details, but there's several other programs also looking at very high brake thermal efficiency. Generally speaking, and I think Mr. Chiatti did a nice job of kind of breaking this down, there's a fuel energy input, There's a lot of different ways to address this particular problem, but whether you're looking at an opposed piston engine, a variable compression ratio, a split cycle, rotary engine, basically you're trying to just get more usable work out of the engine, whether that's through an improvement in combustion losses, heat transfer losses, exhaust losses. You're basically attacking any of those losses that are not directly contributing to brake thermal efficiency. So lots of different approaches, lots of different strategies, but they're all basically focusing on minimizing engine losses. Real quickly, I'll talk about some of the work that I'm going to discuss today. The way these consortium work, I'm not allowed to tell you the latest and greatest activity because it's a private consortium, but they do allow me after a few years to go ahead and present some of this activity. So the work I'm going to be presenting today is primarily from our CHETI 6 consortium that occurred 2011 to 2014. At the point in time, there was a lot of discussion in the industry. There was kind of a two-pronged approach. A lot of people were looking at cold combustion, so these might be things considered RCCI, very dilute combustion, basically trying to minimize the effective combustion temperatures as a potential pathway to very high efficiency. There was also some in the industry that were thinking, well, we've got these new SCR systems, they work quite well, why don't we relax the engine out NOx constraints, let the engines get a little bit hotter, and try and look at, can that be a potential pathway towards very high brake thermal efficiency. On the CHETI 6 program, we actually addressed both of those, looking at two different ways. We also took a look at boost systems and friction reduction. Last year, I'm just going to provide like a one-slide recap. Last year's presentation, I actually talked about the hot combustion, where we took a look at several things towards the hot combustion path. Some key technologies were low heat transfer combustion system, trying to look at both passive and active ways of trying to reduce insular heat transfer. So technologies such as the thermal swing coating, thermal barrier coating, changing the piston temperature fundamentally, looking at very high piston temperatures. We looked at very high efficiency boost systems, friction reduction, all of those types of activities. And you can see in the lower right-hand plot there, the overall final demonstration was around 48.5% brake thermal efficiency. So back in 2014, a pretty reasonable result for high efficiency. Today's discussion, I'd like to talk not about the kind of hot combustion, which was the Cummins ISX there, but actually about some of our cold combustion activity. So our cold combustion activity, our dual fuel activity, took place on a couple of different engines. I'm just showing them there because I've had some good photos. We'll start with the engine that was based on a Navistar engine. This is a 13-liter class diesel engine, common rail. We heavily modified the engine actually. So we left the fuel system in there, but we replaced many of the other components, piston, bowl, injector, turbochargers. We added a dual loop system. We rematched with a high efficiency turbocharger. We had both port fuel injection for when we wanted to evaluate low reactivity liquid fuels. And we also had we added a single point induction system for CNG, which is indicated on the schematic there. So we modified this engine quite heavily to be able to enable looking at some cold combustion. So as I mentioned, we did quite a bit of work. Early on in the program, there was a big question about if we're going to look at cold combustion, what's the right combination of fuel, mixtures. We looked at different things like different octane gasoline, 87, 92, 105. We also looked at things like E85. In addition to gasoline, we looked at compressed natural gas, so methane or line gas, depending on the thing. That had the potential advantage of it's a very knock-resistant fuel. I think one of my colleagues once said if methane wasn't flammable, it'd be inert. So it's a very knock-resistant fuel. It's a very interesting one to use for these types of dual fuel combustions. On the igniter side, so this is the high reactivity fuel that we looked at. This was the one that was being direct injected. We looked at a few different fuels, looking at JPA, diesel fuel, GTL. We looked at various delivery methods on the fueling system. On the boosting side, we looked at single-stage turbochargers, dual-stage turbochargers, combination of turbochargers and superchargers. EGR systems, we gravitated towards dual loop because it gave us a bit more flexibility. And then we did a whole bunch of work looking at different compression ratios, different bowl shapes, different types of bowl geometries. A lot of work that occurred here. I'm going to try and highlight a few of them, and I'll apologize if there's some gaps in the story just because in the interest of time, I wanted to try and make it a little bit concise. But mostly this slide was just to say we try to explore the space pretty well. One of the reasons we explored the space so well is in our consortium, as I mentioned, we have a lot of different OEMs, we have a lot of tier 1 suppliers, and when we were introducing this dual fuel topic, there was a lot of research being conducted. And in the literature, there are several papers that were touting RCCI as a potential pathway to high efficiency, sometimes reporting 50, 55, 60% gross indicated thermal efficiency, sometimes even higher. So the real question from our consortium members was, are we missing anything? We need to explore this potential pathway. Is RCCI really the pathway towards the future? At this time, I'm not sure if any of you guys remember, but oil prices were very high. So there was a strong drive for looking at engine efficiency. Some of the OEMs really didn't like the idea of dual fuel. I think maybe some people have mentioned that they accepted DEF and they accepted 2 fluids, but they sure as hell weren't going to accept 3 fluids. So pick your favorite 2, whatever you need to do. But for research, they allowed us to look at 3 fluids, and in this case, we went kind of explored it. So because there was some literature reported, they asked us, a lot of this research is a little bit fundamental, a lot of it's being conducted on single-cylinder engines, and the question was, does that really translate to multi-cylinder engines? And if it translates to multi-cylinder engines, is this combustion pathway feasible for full load operation? What are some of the implications on the boost system? How does it operate at low load? There's some challenges with low load operation sometimes with these RCCI type combustion modes. So they kind of challenged the Southwest research team, go explore all these things and report back and tell us what you find. So our approach was, we took a look at the literature. This is one of the examples of the papers that we looked at. There are, of course, several papers that were published. This one in particular was quite good because it was quite comprehensive. It provided quite a bit of experimental details as far as the experimental setup, the boost system requirements, EGR setups, and those type of things. And I'll highlight in the top right there, it actually showed one of those keys that were kind of exciting the industry at the time. It showed an indicated efficiency of around 57%. And that actually wasn't even the highest one that was presented in this paper. They actually showed one that was touching right on 60% if you decrease the in-cylinder heat transfer losses. So you can see why the industry was a little bit enticed by this RCCI, very high gross indicated thermal efficiency. So our challenge, we studied the literature, we took a look at it, we tried to match it up as closely as we could on a multi-cylinder engine. In this case, we were fortunate to see the combustion bowl shape that was published in the paper. We happen to have a bowl shape that was quite similar and had a very similar compression ratio. And so we took a look at the paper, we started modifying the engine to try and match these conditions that were published, to try and see what type of results we were able to achieve. A little bit of a challenge. Our engine actually had a real turbocharger, and at the point in time when we were doing this experiment, it had a 2-stage turbocharger with high pressure and low pressure EGR, but we needed to match the experimental results that were published in the paper with a single cylinder engine. So the turbocharger was not a perfect match. The way we overcame this is we actually had an auxiliary boosting system that boosted the intake of the low stage compressor. Now, that might be considered cheating by most, and I would agree. The way we made sure that we weren't cheating is we actually had hardware in the loop. So we had a GT power model of the engine with real turbochargers at the test cell. Our approach was we were using the GT power model iteratively at the test cell to ensure that as we were increasing the boost targets, matching the EGR targets that we saw in the single cylinder research paper, that we were also appropriately back pressuring the engine based on the temperature that we received at engine out to make sure that we were closely accommodating what a real turbocharger system might have. So it's a little bit complicated because we weren't able to just run it like a single cylinder engine, but we tried as best as we could, represented it. A couple of details about the GT power model. It also simulated a 2-stage boosting system. We assumed a 75% combined efficiency, which was similar to the assumptions that were presented in the single cylinder research paper, and we tried to match up everything else as best as we could. Long-term takeaway, if you look in the top right-hand picture there, you can see a comparison of the apparent heat release rate. Now, this has actually been normalized to the cylinder volume. Our engine was a 13 liter. They were modeling the piston bowl, or a bore of a 15 liter, so there was a slight difference in the displacement of the engine, but as best as we could tell, it matched up as closely as we could to the apparent heat release recorded on our multi-cylinder engine. Okay, great. So we've now matched some literature. What did we learn? Well, we didn't quite get to 57% gross indicated thermal efficiency. The bar chart on the right-hand side, I'm going to draw your attention to the left-hand bar. These are all experimental results from the multi-cylinder engine, and we try to match up the fee equivalent. So this is a fee that takes into account the EGR level in addition to the dilution of the paper. We try to match the IMEP as closely as we could, and we try to match the fueling as closely as we could. What we achieved was around 53% gross indicated thermal efficiency, which is quite good. But the problem is to achieve the pumping work targets and the EGR targets required to get there, we found that the boosting was much more of an effort than what the single cylinder engine paper had published. So if nothing else, a cautionary tale when you're doing your single cylinder engine work, be skeptical of the boosting system. It's pretty easy on a single cylinder to just boost it up as much as you like. When you try to go to real turbocharger systems, there's some challenges. So, did we get to 57% gross indicated thermal efficiency? Sorry, the answer is no. But this was an important result to some of our members because they were looking at chasing that 57% indicated efficiency. And seeing some of these results, they said, well, we didn't quite get to 57. And more importantly, when you look at the brake thermal efficiency, we're on the order of 41.6, 42, which is still a reasonably good number for part load operation, but we're not in the 50s. So this is our target. We're trying to find technologies that can push high 40s, 50% brake thermal efficiency. So there's a couple other examples. We moved up and lowered a little bit, and I don't think I have a pointer, but as you move to the right, we're actually now changing, the right two bars, we're actually changing the boost system and EGR targets. So look at some different dual fuel strategies that Southwest was interested in doing. And if you look at the very far right-hand bar, that was one of our better results. And so this isn't exactly apples to apples. This is a higher DMEP. We're at 19 bar DMEP now, and we're using a different combustion strategy. We're using slightly different fuels, but I just wanted to highlight that the dual fuel combustion is, in fact, quite a good combustion concept. You can see we're not achieving that much better gross indicated thermal efficiency. In this case, around 54 gross indicated thermal efficiency. And now when we look at the brake thermal efficiency, we're touching almost on 48% brake thermal efficiency with the dual fuel engine. So dual fuel can be a very good high efficiency engine combustion strategy. It's just, you've got to really kind of balance out how much are you going to force into the very, very lean type conditions versus how are you going to balance it out with maybe a moderate approach to it. Okay, so a little bit more detail. I really enjoyed this slide just because for me, it kind of painted the picture. It said, depending on what your goal is, if your goal is to achieve very high gross indicated thermal efficiencies, boost like crazy. That pumping work actually shows up as higher gross indicated thermal efficiency, so the more you boost, the higher your gross indicated thermal efficiency. So if your goal is to show high gross indicated thermal efficiency numbers, no problem. But when you're looking for brake thermal efficiency numbers, which is what multi-cylinder engine guys really care about, you've got to balance that out a little bit. You can't go quite as extreme. You've got to be a little bit more moderate in your boosts and your EGR targets. So if nothing else, this is kind of a nice picture schematic that kind of shows the trade-offs that were occurring in some of the experimental work. You can see the red line shows the pumping work, and as you go to very lean conditions, of course pumping work goes up. And if you go very extreme, then combustion losses become a problem. But anyway, I thought this was a nice kind of colorful schematic to show approximately where we find the brake thermal efficiency optimal from some of our previous work. I wanted to touch a little bit on some of the dual fuel work that we actually conducted. We did find that RCCI was a good combustion mode for some operation. In our findings, when we were looking at the different fuel combinations, we actually found that natural gas was a better low reactivity fuel because it required less EGR to suppress the combustion before you wanted it to occur. So in this example, we're looking at a fumigated natural gas system, and we're looking at a couple of different combustion modes. I tried to highlight them with the little dashed box lines, but sometimes for this particular engine where we're going to be running an RCCI or highly premix mode, where we're going to fumigate the natural gas, we're going to have several injections to try and prepare the mixture. That way near top dead center reactivity takes control of combustion, and boom, away you go, high efficiency. That works up until a limit. Later at higher VMEP points, we found that a different strategy had a little bit better combustion, and we call that our pilot dual fuel. The main difference between this is we're we're not quite as premixed in the sense that we are maybe putting in 1 or 2 early injections to try and prepare some of the mixture, but we're not letting that mixture become so reactive that it's going to go off based on kinetics only. In this case, we actually have a diesel injection near top dead center that provides a much better combustion phasing control. That was pretty important for us as we move to very high load. We want a little bit more stable combustion. We want to be able to maintain combustion phasing control. It had a little bit higher NOx. That was a trade-off that we were willing to accept to just try and say, we're going to have a little bit better control of our combustion phasing by taking this type of approach. This pilot dual fuel combustion was a little bit different than RCCI in the sense that it wasn't just driven by reactivity. In this case, we really do have this diesel injection that's initiating almost a flame front propagation of combustion. And so you can see here in this wonderful convergent science animation that was generated, the diesel injection very clearly, and then if you look at the mass fraction of methane, you can see that there's a flame propagation that's occurring. You can look at the chemical heat release, you can see that it's actually progressing relatively quickly towards the end of combustion. This was one of the bowl examples. This wasn't the final bowl that we selected, but this was more of just a visualization of the difference between RCCI and this pilot dual fuel combustion mode. Plus, everyone likes a CFD animation, right? Okay. So I wanted to highlight that in some of our research, we were tasked also with looking at what are some full load opportunities, what are some part load opportunities, can we have a full RCCI engine? Based on our research, it would be challenging. So one of the things that we actually implemented was multi-mode combustion for part load, where we can have a lot of problems with over-dilution and combustion stability. We have a diesel injector, let's just run diesel at the low part of the engine map. The mid part of the map, RCCI, seems like a good solution. So when we have enough boost system and we're not over diluting the system and all of the trade-offs kind of work out, we're going to use RCCI because it provided a little bit better NOx and DSFC. And then the high load, we actually used our pilot dual fuel strategy. So I'll highlight a paper that one of my colleagues is presenting sometime during the SAE conference. I can't remember the exact time, but there's a paper number there in case you guys are interested. That was just some of our findings. We were able to actually, the black line that's with the dots is actually the baseline torque curve from the 13-liter engine, and you can see that we're able to achieve similar torque curve in this dual fuel type operation. So, is it a future pathway? Maybe. It shows some pretty good high efficiency. There's some NOx advantages to it. There's some challenges associated with it as well. We did have better combustion phasing control when we used the pilot dual fuel, but transients are going to be a challenge in the future. So, but nonetheless, some interesting things. I still have a little bit of time, so I'm going to talk real briefly. This is a cylinder pressure heat release trace from one of our high efficiency points. In this case, it was 47.8% brake thermal efficiency. The energy breakdown shown on the right looks pretty good. It's got a high BTE number, but I want to highlight the combustion losses are outrageous. This is at 2.4% combustion losses. And I'm sure I've got some combustion guys in the room. The first rule of combustion, burn it in cylinder, right? So this is a big challenge for us moving forward. We achieve very high efficiency. It'd be even better if we burned all the fuel in the cylinder, right? So during the program, we wanted to look at some strategies to decrease combustion losses on a fumigated dual fuel engine. We conducted a pretty big study actually trying to understand where are these combustion losses coming from. There's an SAE paper that was presented earlier this year that kind of highlights some of those differences, but we identified 3 main combustion losses were occurring on this particular engine. There were crevice losses, bulk losses from overleaning, and some load losses. One of the easy ways, at least for me, is we stole a little bit of ideas from the gasoline guys. The gasoline guys have to deal with combustion losses a lot more than the diesel guys, and one of the ways that they do that is they address the location of that top ring. Basically, let's try to eliminate some of the in-cylinder crevices that occur. Turns out that works out pretty well even in a diesel engine. So there's a few other strategies we discussed in the paper, but really for dual fuel engines, if you're going to continue to fumigate, this is going to be a continued challenge. You got to burn all the fuel in the cylinder, right? Okay, so another strategy that I'll briefly touch on, if you don't want to address your crevices, then maybe another alternative is to just direct inject the fuel. We did a little bit of a study on this, so in this schematic I wanted to just highlight the differences between a couple of our dual fuel engines. On the top, the Navistar 13-liter engine, we used a fumigation system. We looked at a couple of different combustion strategies that I briefly discussed. In another program, we had access to an HPDI engine. This was a Westport engine that uses their dual needle injector. It traditionally uses kind of a slow combustion. So in the stock configuration of this HPDI engine, you can see that the diesel injection occurs first, and you can think of that as it's going to be a great spark plug, and then they just spray natural gas into that flame. It's very good when you want to burn a lot of natural gas and you want to use very little amounts of diesel. So because the diesel is basically only there to start the fire, and then the natural gas that's direct injected is burned in a diffusion flame. One of the trade-offs is this particular fuel system is only capable of around 300 bar injection pressures. So when you consider the fact that you are going to inject at 300 bar, you can imagine the combustion durations are quite long. That's a disadvantage. So one of the things we explored on our program with this engine was to try to look at, again, taking some of the things we learned from our other dual fuel engine and applying those combustion strategies. In this case, let's premix the fuel. Let's put in some natural gas before we inject the diesel, and then use the diesel as kind of the spark plug after we've highly premixed the fuel. Turns out that works pretty well. Engine experimentation, again, 15-liter engine, all the specifications are there, uses their HPDI injection system. We left most of the turbocharger and the after-treatment system. This was just a quick study looking at the combustion system. Very briefly, I'll mention this is another schematic showing the difference between the stock HPDI configuration, where there's the diesel injection first, followed by the natural gas, that's indicated by the blue box, and then the DI squared, as we call it, or dual direct injection dual fuel approach in the orange box that we're showing here. Now, one of the keys here is we were required to change the targeting angle of the direct injection natural gas because we are going to be injecting very early in the cycle, and if you don't want it to just hit the walls, you've got to adjust that targeting angle quite a bit, so that way it's hitting more in the center of the bowl and you're not just, packing the crevices. But other than that, it's pretty straightforward. So I'll get to the meat and potatoes real quick. This is a very high-level overview of the resulting combustion losses. And on here, I've got several different strategies. On the top, diesel only, purple line, of course, the diffusion combustion, it's direct injected. We have very high combustion efficiency as expected. The HPDI, excuse me, also very high combustion efficiency, as you'd expect. One of the challenges that I'm also showing, excuse me, on this plot is that green line. Now that green line provided the best brake thermal efficiency on our multi-cylinder engine, but you can see that the combustion losses are kind of ridiculous. 2 to 3% at different points. RCCI is also shown on there, so at a little bit lower load, we have an advantage in combustion losses by using RCCI combustion. And then I'm showing the key here is that red line. And you can see by taking a dual direct injection combustion system, we're able to kind of mix between the two different worlds. We have a combustion that's very fast and very efficient, like RCCI, but we don't have the same combustion losses as some of those RCCI points. So the dual direct injection seemed like kind of a Goldilocks type of case. If you can direct inject the fuel, that gives you a little bit more flexibility as far as when you introduce the low reactivity fuel. If you can adjust the targeting angle, you can avoid crevice packing, you can avoid combustion losses associated with that particular mechanism, and you can still get some high efficiency. So something we're looking at into the future. Okay, and there's a little box. I'll again highlight, I think I put this slide in here twice, so I'll apologize, but there's an interesting paper coming up. So where does that put us? I wanted to put in this slide just to kind of highlight where we're at with the greenhouse gas phase 2. When you look at that solid red line and that blue line, that looks at kind of some of our early work on the hot combustion, both with a regular torque curve and a downsped torque curve. And as Steve kind of mentioned, downspeeding does provide a BSFC improvement. So when you consider that solid blue line there, that's the Cummins ISX hot combustion, and you can see that we could achieve 2027 greenhouse gas today, at least theoretically. We don't build engines. The dual fuel engine, it's a little bit more complicated in the sense that combustion losses do have a pretty strong impact on greenhouse gas. As I mentioned, we're using natural gas, mostly methane. When you consider methane, that is regulated like a greenhouse gas. Every gram of methane that you produce has a global warming potential of 34. So you multiply that gram by 34 and you add that to your CO2. So you can see when we look at the engine out emissions, they look like they're fantastic. They're in the lower left-hand corner. When you consider the methane impact of those on greenhouse gas, it makes it a little bit worse. But we still have some considerable margin to the future greenhouse gas standard, so we feel like we're in a pretty decent spot. So all this research was a little bit interesting, good potential. Our target was 55, the engine was around 48, so we had some good potential from the engine. We still need a little bit more, so the work continues. There's also the challenges with low temperature combustion and after treatment that I'm not going to discuss today. But I will mention, just because Steve made a nice plug for us, waste heat recovery is another area of interest for Southwest Research Institute. Like I said, I have 26 bosses on this consortium. Half of them are already doing organic Rankine waste heat recovery. So they gave us a challenge. They said, we want you to do waste heat recovery, but we're not going to let you do organic Rankine. Okay, fair enough. So I looked around at Southwest Research Institute. It turns out we have a group that's heavily invested in supercritical CO2 waste heat recovery. In fact, we recently received a $100 million program to demonstrate this technology on a power plant that's being built down at Southwest Research. So it's a power plant waste heat recovery system. One of the keys that I like to point out to people, and I think I've got a bigger picture here, is that guy. That guy over there is holding a big turbine shaft. That turbine shaft is 10 megawatts. So you can imagine the power density associated with this waste heat recovery system. It's very power dense. The other advantage is, as Steve mentioned thermodynamically, it's a little bit more efficient because we're not doing that phase change. The entire system stays supercritical, so we have a higher potential efficiency associated with this particular waste heat recovery system. So high efficiency, very power dense, sounds pretty good. One of the challenges is scaling. When you consider a 10 megawatt system that a guy can hold, and we think about what do we need on a heavy duty truck, maybe 50 kilowatts or something like that, when you scale that turbine down, pretty soon your turbine is the size of your pinky finger. Now, that's going to be a problem. Anybody that's done turbine design knows that when you have turbines that are this small, the tip losses are astronomical. So your efficiencies with a supercritical CO2 turbine that's the size of your pinky is going to be a problem. The truck guys would love it for packaging, but there's going to be some challenges there. So some of our current research is actually looking at how do we get away from my pinky into something that's a real device, and we're looking at other types of expansion devices instead of turbines. So I think my colleague Tom Briggs has maybe talked about that in previous symposiums, so I'm not going to dive too deep into those details, but that's an active area of research for Southwest Research Institute. Okay. Finally, I just really like this logo. You know, we're starting our new program this fall, so I just wanted to splash it up there. Chetty 8 is coming. If anybody's interested, I can provide some more details, but at least the logo looks nice. And with that, I think I'm a little bit fast on time. I had a lot of coffee this morning, but I welcome any more questions, or if there's a discussion over the coffee break, I can join as well.
Are there any questions for Jason?
Hello, my name is Frank Willems from TNO Automotive in the Netherlands. I have a question related to the advanced combustion concepts and their control. If you talk about combustion phasing control and other types of control, you would anticipate the availability of cylinder pressure sensors in the field. So thinking about durability and availability, what is your opinion about that?
So cylinder pressure feedback would be an advantage to many of these RCCI type combustion, dual fuel combustion, having that feedback in real time would certainly allow us to go a little bit closer to that knife edge to where we're about ready to fall off into either knock or unstable combustion, those types of things. So it could be an advantage to have that type of feedback. One of the challenges that I see with RCCI, and especially when we move to high loads, is you have to take drastic changes in your fueling and EGR strategy to be able to control combustion phasing. So if you want to advance combustion phasing by 1 degree, you may have to change your injection by 20 degrees or something like that. So even if you have the feedback from advanced sensors, there's still the controllability of the combustion itself that is a challenge. So that's why at some loads we were using that dual fuel pilot combustion strategy, because it gave us a little bit more control over combustion phasing. Not perfect like diesel, but a little bit closer to diesel.
Another question is related to the natural gas concept. Do you foresee any challenges related to the quality of the fuel, so changes in fuel quality in natural gas?
Absolutely. So depending on what methane number you're looking at for natural gas, we've seen in several of our studies that has a big impact on it. We haven't fully addressed those in any of our studies. Most of ours are just looking at, okay, is the combustion worth it? And then later on we can address some of those kind of production problems or things like that. Now I will say that combustion strategy has garnered a little bit more interest from some of the people that have engines that aren't as transient or maybe are for stationary power, in which case, you don't have to worry as much about transients as far as driving a truck. And those type of applications, maybe that combustion mode would be appropriate, and some of those you have GC feedback on the type of line gas that you're getting and understanding how much propane, ethane, all that type of stuff is in the natural gas. So it is a combustion concern. Is it something we could probably address maybe in the future? But a good point.
Okay, thank you.
Any more questions? Let's thank Jason again. Thank you very much.